Hello and welcome to this tutorial video in which you will learn how to develop a federated app in a few easy steps. To implement a new app, you can use the FeatureCloud App New command. For that to work, you first need to install the FeatureCloud pip package. To do so, just enter pip install FeatureCloud. Now you're good to use the newly installed FeatureCloud command. Enter FeatureCloud App New and append the name of your app. In our case, LR-demo. What happens now is that a FeatureCloud default project gets cloned onto your machine into the specified folder, which is identical to the name of your app. So in our case, we should soon see a new folder called LR-demo inside the FeatureCloud folder that you can see in the terminal window. Now you can open the newly created folder in your favorite IDE. For this tutorial, we will use PyCharm. FeatureCloud apps in most cases are state machines. We can put all our state implementations inside the states.py file that should be already inside your project. But before we begin, we first install the requirements from the requirements.txt file so that the IDE can provide you support. Before we continue, let me increase the font size a little so that you can read the code better for the remainder of that video. Before we actually implement the logic of our app, let's first think about the states we are going to have. In our case, we want to implement a simple federated linear regression, and for that we need 4 states. An initial state, a compute state, where every participant locally trains a linear regression model, an aggregate state, which is only accessible to the coordinator and which is responsible for aggregating the local models, and a write state, where we actually use the trained model to predict values based on previously provided files. We also need to specify the transitions which are possible from one state to another. You have to do that inside the register method that is required by each app state. I will now add classes for each of our states and speed up the process a little for you. After we've created the state classes, we now need to specify the state transitions, which means that we need to specify from which state we can transition to which other state. Some transitions are specific to a particular role, so for example, they are only possible for a participant or a coordinator. Let me now add 2 additional constants which contain the internal paths for the files that we are going to read later or write later. These paths are available inside the Docker container and are prepared by the FeatureCloud system. Now that we've created the state classes and specified the state transitions, let's actually perform some transitions from states. In order to do that, you just need to return the name of the state you intend to go to inside the run method. So in this case, we instantly transition to the compute state from the initial state. I will now add a few more transitions and a few log messages so that we can actually see something happening before we run our first test. Let me again speed up that process a little. If you want to do a transition only if you're the coordinator, then you can use the self.isCoordinator variable, which is true only for the coordinator. In this case, we go to the aggregate state from the compute state only when we are the coordinator. Now we should be good to run our first test. In order to do that, we first need to build our app. You can use a FeatureCloud command for that, which goes FeatureCloud App Build. By default, it will use the name of the directory and tag the image with that name. This name we can now use in the test environment to run our test. So we enter lr-demo, which is the name of the directory and the name of the image. And we also need to provide directories which contain the test data that we want to provide our containers with. Then we press start, and after a while we can see the containers that have been started, one for each participant that we specified before. For each client we can also see the logs, so we should see the log messages now that we added to the code before. Since everything seems to work as expected, we can now go back to the code and continue with our federated application. As a next step, we want to specify the maximum number of iterations we want to perform as a preparation for the later actual computation. When you want to store variables and make them accessible across states, you can use the methods self.store and self.load. The self.store method expects a name, in this case iteration or max iterations, and a value. The load method simply expects the name of the variable you want to load. So here we load the variable iteration and store it in the local variable iteration. We increase the iteration by 1 and store the new value back using the methods I just introduced. Let's finally also print the number of iteration to the log messages, and then, depending on whether we have reached the maximum number of iterations or not, we go to the write state or remain in the computation loop as before. So depending on whether we're a coordinator or not, we either go to the aggregate state or remain in the compute state. Now it's time for another test to see if everything works as expected. So we need to build the app again and then go as before to our test environment. In the test environment, we can just press create again and hit start, because all the settings we chose previously will remain there, so that we can simply start the test quickly and easily. And after a while, we can see that our apps, as expected, go to the terminal state after 3 iterations. So we can see iteration 1, 2, and 3 here in the log messages, and both containers end up in terminal state. Before we continue implementing our app, let's have a look inside the data folder that we provide our app containers with. These data folders contain a so-called config.yaml file containing parameters that are important for the execution of our app. This includes the source file, the target column, the separator, the maximum number of iterations, and the file we intend to write our results to. To read that config file, let's now first install a pip package called BIOS. Do not forget to add that package also to your requirements.txt file so that the app container can be built correctly. We can now read the contents of the config.yaml file by using the bios.read method. Remember that this file will reside inside the input directory inside the app container. We previously stored the directory inside the input_dir constant that we can use here now. All the values of the config.yaml file are now inside the config variable here. Let's now store the contents of this config variable inside our global variables using the store method that we've seen before. Let's fetch all of these variables and print some of them to the log messages so that we can see that everything works correctly. After we've done that, it's time for another test. Once the containers have been started, we now look at the log messages to see if the maximum number of iterations has been read correctly. And as we can see, indeed, here it says max iterations 10. So we can apparently properly read the config.yaml file. Perfect. Now, as a next step, let's actually start with our linear regression. We are going to use a standard implementation of linear regression and federate it. For that, we use pandas and scikit-learn as pip packages that we add to our apps as before. Now the fun part begins. First, we need to read the input data that we will use to train our linear model. Then we need to prepare an initial model that is just basically empty and contains the structure of our model. The structure is the same across all participants so that we can aggregate all local models into one global one. So let's start by loading the data. We use pandas for that. Since our data is stored as a CSV file, we use the read_CSV method from pandas, and we need to specify, of course, the input path and the separator that separates values in each row. We have loaded all these variables before, or we have stored them as constants. So we use our input directory, append our input file variable that we read from the config YAML, and we specify the input separator as a second argument. We then store the data frame so that we can use it later in the compute state. We also create our initial model now. For that we use the linear regression class from scikit-learn. We feed it with the data that we just read. So we hand over our data frame and apply a few modifications to it. Basically what this line does is split the data frame into our training features and our target column. We use the fit method from the linear regression class to start a first training iteration, and we store the resulting model as a global variable like you've seen before. The coordinator then broadcasts this first model to the other participants so that they can use it to update it with their local training data. For that, in the compute state, we first need to receive that global model that has been sent around by the coordinator. This also goes for further iterations, because after the first iteration, the coordinator will aggregate all the local models and send around a new global model. So we basically ping-pong between the compute state and the aggregate state. If we are the coordinator and remain in the compute state and wait for the coordinator to send around a new global model if we are a participant. For a new iteration in the training process, we of course need our data again. So we use the previously stored data frame and call the fit method again. We then also want to score our model after we have trained it in a new iteration. So we use the score method and print the result to the log messages. After we've added some log messages to see what's going on, it's time to start a new test. After a while, we realize that we actually never really leave the compute state. So why is that? Well, at the beginning of the compute state, we expect a new global model to be sent around. But at this point, the coordinator does not aggregate anything and does not distribute a new model. So what we need to do next is actually implement the aggregation state. But before, we need to send around the local models. Well, actually we need to send the local models to the coordinator, who is then in charge of aggregating them. We can use the sendDataToCoordinator method for that. We use the coefficient and the intercept vectors and add them to our data array. And this data array will arrive at the coordinator. We can use the self.aggregateData method in order to automatically receive the already aggregated data. The advantage is that you can automatically apply secure multi-party computation to this kind of aggregation. Now that we have the aggregated coefficient and the aggregated intercept, we can calculate the federated average of the two by simply dividing it by the number of clients. You can use the length of the self.clients array for that. This array contains the client IDs for all clients that are part of your federation. We then also use the current iteration number in order to determine if we are done with our computation, and we broadcast the new aggregated model to all our participants using the broadcastData method. Let's now structure the code a little and add a few log messages before we start a new test. And indeed, after a while we realized that everything works as expected now. The local clients calculate a new local model, send it to the coordinator, which then aggregates it into a global model, broadcasts it back to the clients, And this process goes on for 10 times until we determine that convergence has been reached. Now the only thing that's missing finally is using the global model to predict data. That's the final step we're gonna implement now. So first we need to store the model that we calculated in the previous step. Now that we've stored it, we can load it in the write result step and use it to predict values. So we load the model using the self.load method. We also load the target column as before, and this time we don't need the model.fit method, but the model.predict method. The signature is similar to the .fit method though, so basically everything you see here is more or less what we've already seen. Obviously we also need to load our data frame, but that we have done already in the compute stat. Now finally we write the results again in CSV format, but this time into the output folder, of course. For the output folder we also have a constant that we've defined at the very beginning of this video called output.dir, and the file name is stored in the output file variable. Now let's just add a small log message, and with that let's start our final test. And voila, we can see the traffic log here, which behaves as expected, so it's an alteration between broadcast and gather. And after a while we have reached our 10 iterations, and we can take a look into the final results folder. So once the whole computation is finished, FeatureCloud will prepare the results and zip them into 2 archives. So in this case 2 archives, 1 per client each. And this zip archive for our implementation should now contain the predict file. So let's just wait a little, download the results and open them to verify that everything works as expected. And this is basically our results now. It contains 1 value per sample, and this can now be used for a successive app that is composed in a workflow. So for example, you could use that now to determine how well your algorithm performs by applying an evaluation app to that results. I hope this video has shed a little light on how you can implement an algorithm for FeatureCloud, and a few things have become more clear to you. If you have any questions, use the comments section or write us an email. We're happy to hear from you. Thanks for watching.